So let's continue. So now in what I will discuss in the sequel will be only considering one point vortex in a bounded simply connected domain. So before we had this complicated system for n point vortices, but we take just one, and so you don't have the interactions with the other points. So this term there is nothing. And the self-interaction here with the point with itself is just the interaction of the single point with itself, so just one. So the dynamics, as we have described here, is Hamiltonian and is related to this function, which is called the Robin function, and which is the trace on the diagonal of the smooth perturbation of the logarithm for the green kernel. I recall that it is given by this expression linked to the conformal radius, which is a quantity of interest in complex geometry. So when you have one point vortex, the image of the Hamiltonian is given by an interval of this form, which is minimal value and which goes to infinity, because here, as you can see, so phi, I recall that it is the conformal mapping given by the Riemann theorem. So you send your domain D to the unit disk, and actually the boundary of the domain D is sent to the boundary of the unit disk. So if you take a point Z on the boundary here, the modulus of phi of Z will be 1, and so this quantity will be 0. And so when you take the logarithm, it will be infinity. So you see that you reach the Hamiltonian as reaches infinity at the boundary. And the minimal value is associated to a critical point of this function, which always exists since you go to infinity at the boundary. So there is at least, by compactness argument, a minimal value, and which corresponds to a critical point, of course, and the critical point is elliptic. And you have this minimal value here. So the set of critical points, as we said, we will denote it CD in the sequel. Sorry, it is the set of the critical values, the Hamiltonian. So when you have a critical point Z, the image of Z by the Hamiltonian is a quantity lambda. And so this is the set of critical values. So the values of the critical points. Okay. So the dynamics is given by this. So I just write the grad perp in a complex formulation. So you see here that, for instance, so here you have a dynamical system in C. And when you study a dynamical system, it is important to understand, for instance, the critical points here of the Hamiltonian, if it is Hamiltonian. So you compute the gradient here, and the gradient of the Hamiltonian RD is given by this quantity here. Okay, the set of critical points, if you have a convex domain, for instance, the critical point here, given the minimum of the Hamiltonian, is unique. There is only one critical point in convex domain. So you can imagine the picture. Basically, this function in convex domain, so you have your domain, you have the minimal value, and it will be something like an elliptic paraboloid, like this until the infinity. So this is the main shape of the Robin function in the convex domain. But of course, if your domain D is not convex, it is rather complicated to describe the set of critical points for the Robin function. Actually, the literature in this direction is not. There are several results, but they don't give a full understanding of the classification of the critical points. So this is also something that limited our work. with Zineb and Taufik. Okay, so if you consider also this Hamiltonian system, this is a Hamiltonian in n equal 2. So the n that I mentioned is not the same n as this one, is not the same, is the dimension where lives z. So it's in R2. So when you have a Hamiltonian from R2 to R, it is well known that it is completely integrable by the Arnold-Liouville theorem. And so actually the trajectories can be parameterized. And they are, in this case, closed curve with a period T lambda. And the period with an argument coming from Stokes' theorem. And if you work with the Liouville 1 form associated to the volume form, you can prove that the period T lambda is linked to the area of the enclosed domain. So to recall here, I consider one point vortex evolving in the domain. And actually what I'm saying is that the trajectory of this point vortex, will be a closed curve. And so since the curve is closed, it has a period. And the period is linked to the area of the domain inside the domain described by the curve. Okay, and the lambda here is the energy level of the Hamiltonian. So for each energy level, I have at least one periodic orbit associated to it, or almost all of them. And I can describe the period that the point vortex needs to come back to its original position with this formula. And we can give actually also asymptotics of this period if we are near the boundary or if we are near the elliptic critical point. So for instance, the one realizing the minimum of the Hamiltonian. So near the boundary, you have this asymptotic, which tells you that, so here you have the length of the domain. Gamma is the strength of the point vortex here. And you have this exponential here. So it tells you that when lambda tends to infinity, this tends to 0. So the period tends to 0. So basically when I come near the boundary, the period is 0. So I need almost no time to do one period. So actually what it means that I rotate super fast near the boundary. So, and you can quantify how fast linked to the length of the boundary of the external domain. Now, if you're not near the boundary, but you're near the critical point of the Robin function, or a critical point in general, you can, provided that this critical point is elliptic, which means that locally the Robin function will be like a elliptic paraboloid near this point. You can describe the period, and the period is given by this quantity linked here. A and B are linked to the Riemann mapping evaluated at the critical point. So you have this quantity, which we will see in the sequel that are really relevant in what follows. So the fact that this square root is well defined is exactly saying that the point is the critical point is elliptic. So A is greater than modulus of B. When you write what it means to be elliptic, you find this inequality. And so you can describe at least the first asymptotics near the critical value lambda star of the critical point psi 0. Okay, so now we have a good understanding of what's happening. If I have one point vortex in the domain, I have a closed curve, so periodic motion. And what we want to do in the sequel is to find a patch located around this point vortex. And the patch, the dynamics of the patch will be driven by the point vortex. So it will follow the curve, which is the motion of the point vortex. So the main results that we proved with Zineb and Taufik is the following. So it's a bit abstract, this version, but there will be a more practical version later. So you consider a simply connected bounded domain, and you take a range of values for the Hamiltonian far from the minimal one, and included in the set of values of the Hamiltonian which do not meet the critical values. So this hypothesis is to say that basically we want to avoid some heteroclinic or homoclinic orbits. So we have to avoid this set. And we assume the following two conditions. So the derivative of the period, so the second derivative of the area, should be bounded from below in modulus on this range. And the spectral assumption, which means that the spectrum of a certain matrix, which is this matrix, M, which is the fundamental solution of this ODE, with A lambda is a matrix linked to the Robin function, evaluated at the periodic orbit of the point vortex. So if this matrix after a period, so which is called the monodromy matrix, if the spectrum of this matrix doesn't include one, then under these two assumptions, I can desingularize almost all the periodic orbits of point vortices. So each lambda here gives me a periodic orbit. So each level of the Hamiltonian, think about the convex domain. Each slice of the Hamiltonian will correspond to a periodic orbit. And what we are saying here is that for almost all the slices, you can find periodic motion of vortex patches, which whose dynamics is the following. So the patch is, as we said before, like in the theory of periodic rigid motion, like we have 1/epsilon square, characteristic function of a domain of amplitude of radius epsilon, and the domain follows the periodic orbits psi lambda. So you have an epsilon perturbation of a small domain O around the periodic orbit of the point vortex. Okay, and actually you can compute the solution at the first order and see that in time the motion is not rigid. But I didn't write it here, but you can prove it. So these assumptions are quite obscure for the moment, but we will see in the proof where they appear, especially how this matrix, where does it come from?
Emeric, so they are not rigid in what sense? So they're
in the sense that you follow the trajectory, and the motion of the boundary itself of the little patch will move in time.
Okay.
It's not
rotating or so.
It's an oscillation. It's an oscillation. You cannot quantify more. It's just an oscillation. But at least if you're not, for instance, in the unit disk, the motion will not be rigid. This is something that I will say later. But like in almost all the substitution, the motion is non-rigid in the sense that the boundary of the patch moves in time. It's not in a rotating frame. It's stationary. It's moving really in time.
Okay, thanks.
Okay. So, okay, we have two assumptions, quite obscure. Like, where does this matrix come from? We don't understand. So we will explain in the proof later. Before this, I want to mention an application of this theorem in more practical situations. So assume that you have a convex domain D, or sufficient to have just a unique critical point, such that you are sure that this assumption will be verified. I will prove it later. And you assume the following. Actually, the monodromy condition, so the spectral assumption, will be translated into checking in the Fourier coefficients, in the Taylor coefficient, sorry, of the Riemann mapping, or the inverse of the Riemann mapping. You will have a condition of the Taylor coefficient. So the condition is the following. If you take the inverse Riemann mapping, so the one from the disk to your domain, which realizes in zero that you're at your critical point, unique. Then if you compute the third derivative at zero over the first derivative over zero, so the third Taylor coefficient over the first one, if it is not in this set, then the spectral assumption here is satisfied. We will understand it in the proof. And you can prove also this condition with an analyticity argument. So this theorem actually is really practical because you just have to know the shape of the Riemann mapping, and actually not even the complete shape, just the first Taylor coefficients. So in practice, if I give you a domain, you can check easily if this condition is satisfied or not. Easily, more or less. So this quantity, since we have imposed this condition, actually is linked to this quantity here, S of f, which is called the Schwarzian derivative of f, which is defined like this. So f 3 over f prime minus 3 half f second over f prime square. So this quantity tells you that quantifies you how much f is different from a Mobius transform in complex geometry. So the transformation, which are the automorphism of the unit disk. So actually, SF is zero if and only if f is a Mobius transform. So it quantifies how much you're different from a Mobius transform. So here you really have some geometry behind the result here. Okay, the proof. What is the proof? You look at the monodromy matrix at the critical point, which is elliptic, and so you have this condition. So if you take the trace of so checking that one does not belong to the spectrum of this matrix is the solution of this system. And A, as you can see here, if you take the trace of A, since this is purely imaginary because there is an I here and this is real, the trace of A is zero. So the determinant of M is 1. So actually, this matrix M is with values in the special linear group. So you can link the spectral assumption to the trace of the matrix M. And it's exactly to say that the trace is 2 in this case. And you can compute at the critical point what is this quantity, and it is linked exactly to the Schwarzian derivative. And so you have a cosine, which should not be 1. And here there is a belong, not belong. So it is 2 if you belong to the set. So if you're not in the set, you're not 2, and so you have this assumption satisfied. And by an analyticity argument, you can also say, because we know the boundary, the behavior of T at the boundary, as we have said here, so we know that T is not constant. So by an analyticity argument, you can impose this condition also, if you know that there is only one critical point. So that's why there is this assumption. Okay, so it's rather clear how we get this theorem from the theorem before, and this theorem, as we have said, is really practical. But, because there is always a but, if you take the most simple case, like the unit disk, so the Robin function is completely explicit, the periodic orbit for the point vortex is completely explicit, is a circle. Then you want to apply this little theorem, which is good in practice, and you find that is not applied because phi is the identity. You send the disk to the disk, so it's the identity. But S of the identity, since the identity is a Mobius transform, you find 0, and 0 is in this set. So you cannot apply the Taylor criterion here. You cannot apply this theorem, but this theorem applies actually. You can compute explicitly the period and its derivative. You can compute explicitly the monodromy matrix. And you find this for the period. The condition for the monodromy is that the energy level should not belong to this set. So you can apply the general theorem. But actually, for the case of the unit disk, we can do much more. We can have a better result because this theorem tells you that most of the trajectory can be desingularized into periodic motion, non-rigid if you have good condition. But actually here it is rigid because you can prove with the same method as the previous part of the talk. You have one point vortex, you can desingularize it with an implicit function theorem into a rigid body motion. So this patch here, we just rotate around the center here with good angular velocity. And you can explicitly compute the point where you can apply it, the implicit function theorem, and it's related to the bifurcation point of the obtained by Zineb and Taufik and Johan in this. Yeah, actually we recover the case m equal 1 when we put the patch here. When the point tends to 0, we recover the motion, the epsilon patch, the non-trivial patch around the trivial solution given by epsilon d. Okay. And the other branch, we don't see them because with the limit in the limit here, all the branches are sent to infinity. So we can recover only the first branch. Okay. And so this is the bad news, is that if we take the simplest domain ever, it doesn't work. The simple version of the theorem, we have to apply the big version of the more elaborated version of the theorem. But actually, it's not the end of the story. You can apply it to less symmetric domains, because if you try with, for instance, regular polygons, also you will find that S of f is of 0 is 0. So you have to look at less symmetric domains. And actually, if you take, so after the disk, what can you take? You can take ellipses, or you can take a rectangle. And so the result is the following. If you have ellipses of semi-axes A and B, then if the ratio A over B is not in a counter set, in a countable set, sorry. So you have certain values that you have to avoid to satisfy the Taylor criterion. And since the ellipse is convex, the first hypothesis of this theorem, the fact that the Robin function has a unique critical point, is automatically satisfied, also for the rectangles. So you just have to check the Taylor criterion. And actually, the countable set that you find is exactly related to this countable set here. So this is the result. I will give a more precise version after. For the rectangle also, like if the ratio between the small length and the bigger length is not in a countable set, you can apply the Taylor criterion. And you can also apply it to the M sectors. So you take your unit disk and you consider pizza slices of angle pi over M. So you have, for instance, if you take M equal 2, so you have pi over 2. So the unit disk is divided into 4 pieces. So in this case, you can compute exactly the critical point of the Robin function, which is given by this expression. And you can compute explicitly the Schwarzian derivative of f at 0. And its square is given by a quantity like this. So rational numbers times So a rational number times square root of m squared plus 1 plus another rational number. And so in particular, this guy is not rational because square root of 4m squared plus 1 is not rational. And so in particular, since we have the square here, so we take the square here, but if we take the square here, this is rational. So you are not in this set because you're not rational. So you can apply the Taylor criterion also for the M sectors. Okay, so now I want to discuss a bit more about the elliptic shape to give a much more precise result than the one I precised before. So you consider an ellipse that you normalize B equal to 1, and A will be bigger than 1. So you consider an ellipse like this. Then the Riemann mapping has this shape. So Sn is a special function called sinus amplitudinous function, and its first Taylor coefficient are this. K is the Legendre complete elliptic integral that you have. It's given by this. It's well known in the literature, and so you can compute what it means to be in the set S for the Schwarzian derivative, and you find that a certain quantity has to be has to avoid the integers, and the quantity is completely explicit, or rather explicit, but related to the Legendre complete elliptic integral. And so K here is given by this, and there is a bijection between K, which is the argument of the sinus amplitudinous function, and A, which is the largest semi-axis. So you have a bijection between K and A. Yep. So, and this is a condition of on K. So you can describe explicitly the set of A, of the A's that you have to avoid. And so they form an increasing unbounded sequence. So it tells you that for the ellipses, you really have some of them that you have to avoid, but they are really rare. Like you must be really unlucky to find to be exactly this ellipse to not to apply the Taylor criterion. Okay, and then you can ask, okay, but does the general theorem applies in this case? And the answer is I don't know. So, and for the rectangles, I just want to mention that you can completely describe again the points that you have to avoid for the aspect ratio. So they are given by this these quantities here. And how do you find it? That's the point I want to focus on, is that in the case of polygons, the Schwarzian, the inverse conformal mapping is completely explicit and is given by Schwarz and Christoffel. So it has this shape. And so if you compute exactly the Schwarzian derivative of f, in the case of symmetric convex polygons, for instance, you find a completely explicit formula linked to the theta, which describe here. Okay, I should mention this. Like, so you have a polygon with you have the vertices of the polygon, and the map here will send you the vertices of the polygon on 2 points on the boundary of the disk, or rather the converse from the disk to the domain. And the beta here is just to place your polygon in the plane, and the alpha is to delete your polygon in the plane. And this guy is just the image of the different vertices. So you completely describe, provided that you give the mu, which are the exterior angles of the, for a vortex, you have to give the internal angle, and you can associate the external angle to it. And once you give this, you completely describe the polygon. So when you compute the Schwarzian derivative, it's completely explicit related to this theta k and the mu k, which are the exterior angles. And in the case of the rectangles, you can really compute what it is, and you find this condition for the Taylor criterion. Okay. Now that we have, so we summarize a bit, we had the description of the motion of a point vortex in the domain. Hamiltonian system, we have the understanding of the period, we have a general theorem, we have a theorem more practical. It is not applied in the most simple situation, but in rather simple, but not the basic one, it's satisfied. And so now you can apply a duplication method. So if you take, for instance, a rectangle, so you have the rectangle as a domain, you have point vortex inside, which has a good motion. You can desingularize it because for most of you take a rectangle with this condition, you can desingularize into point vortex, into vortex patch periodic motion. And now what you do is that the rectangle has a segment and its boundary, and is completely included into the half space delimited by the line associated to the segment. So what you will do is that you will do a symmetry with respect to this axis, and so you will have two rectangles, and the patch that you had here has a symmetric on the other part. And actually, this is the purpose of this theorem, which tells you that you can define a quantity, omega star, omega hashtag, which will live in the domain, which is the initial domain and the symmetric one, with respect to this line, and is defined by this transformation. So it is exactly omega in the right part, and in the left part is minus omega applied to the symmetric of X, because you have to define it all over D, but omega is defined only on D. So if you're in the symmetric of D, you come back to the D with the symmetry here, and you take a minus. So you can check that this solves Euler equations in the whole domain, so the D and its symmetrics, provided that omega is a solution in the domain D. I don't know if it's clear. You have the solution here, and you can construct a solution in here and the symmetric. So, and you have a change of sign here. So if you had a plus rotation here, it is transformed in a minus rotation here, and you have a dense of two patches like this, which will have periodic motion. Okay, so the proof is to check that omega star is a solution. So it's a computation using the fact that you have a link between the green function of D and the green function when you symmetrize. Well, I don't precise here the links, but if you do the computations, you can find it. And in particular, so this is an existence result, this theorem. So you can construct new solutions in a more complicated domain, provided that you have really already a solution in the first one. And so since it is an existence result, due to the theory of David Chiaravari and Christophe Lacave, you don't need any assumption on the domain to have the well-posedness of the Udovich theory. So you can really have angles and stuff like this. For the existence part, it's not a problem. Just to mention, because when you do the symmetry, you can have some angles which are not good. So it's better to mention it here. So this is, of course, the procedure. If you have domain like this, for instance, you want to first symmetrize with respect to this line. So you obtain, if you had the vortex patch motion periodic in time here, you will have 2 here in the new domain. And you can duplicate again, and you will have 4 point vortices. So if you apply it to the rectangles, so here I take this initial rectangle where I have my patch. I duplicate once, I have 2. I duplicate again, I have 4. I duplicate again, I have 8 and 16 extra. So for the rectangles, it works. For the ellipse, there is no segment, so we cannot apply the method. But for the M sector, you can apply. And so here you had, for the M sector, we said we could apply the Taylor criterion. So for this sector, I have vortex patch periodic motion, and I duplicate and duplicate again. So I have a motion of 4, a synchronized motion of 4 vortex patches in the unit disk. Okay, so this was to explain some applications of the main theorem, but now we will discuss about its proof. So if there is no question, I will get into the proof of the main theorem, which is a bit involved. So if there are some questions, it's better to do it now than after.
Maybe just a quick question. So you are able to describe the motion of synchronized patches. That's what you are telling us here, right?
You can construct them, yes.
Yes, but
It's an
you
existence.
cannot.
You don't describe the dynamics really. You can do it at the first order, but it's an existence result. So you prove the existence of such non-trivial solutions.
Yes. So, but after all, it's all about describing or understanding the motion of one vortex, right? And then you duplicate. That's what you are doing
Yeah,
here.
yeah, yeah. The duplication method, and in the end, you just come back to 1.
One, yeah. Yeah. So, what can you say about if you have 2 points, and so
Yeah.
it's
uh,
not necessarily like, yeah.
it's a complicated question.
Okay.
Like, okay, I have to mention that I said here that if you have 2 points, it's still integrable.
Yeah.
So you can compute the motion, and you can try to describe. The motion will be really beautiful, but for the moment, it's not clear.
Okay, maybe not in a general domain, but what can you say about the disk? So
Eh,
the
That's where you have to start. So you take the unit disk actually, and you take 2 points. So I expect that the motion will be like the leapfrogging of Zineb, but in the
Mhm.
unit disk.
Okay.
So this is something that we would like to do later.
Okay. Oh, and a last question, and I'll let you go. Yeah, so this is on bounded domain. So, what do you expect if you are on a periodic domain? Are things similar or
Periodic domain, a good question. You mean, wait,
yeah, on
uh,
the torus?
on the torus? Okay. Um, I don't know, because when you're on the torus, the Euler equation is modified.
Yeah, sure.
So I don't know.
Okay.
Don't know. Good question.
Okay, okay, okay. It's okay. Okay, you can go ahead. Okay.
Okay. Let's see if there is no other question. Okay. So let's discuss about the proof. So you take an ansatz, the ansatz that is was mentioned in the theorem. So you take a concentrated vortex patch around the point vortex periodic orbit, and you insert it in the vortex patch equation. What you find is this complicated equation. So I call G this what we get. So we have the log and we have the K again, and this is the part related to the point vortex. Okay. And then we take a parametrization such that everything is renormalized with 2 pi. So you introduce omega, which is the frequency of oscillation of your point vortex periodic orbit. And you take a parametrization gamma of the boundary of dt like this. Actually, it should be O, but so gamma here is an epsilon perturbation of 1. So it's parameterization of O here. And with this square root, so it's a polar parameterization of the boundary of O here around the point vortex. So this square root is to find something nice here when you introduce the equation, because it preserves the Hamiltonian structures. Okay. So once you have this, what have we done before? Before we applied bifurcation theory or implicit function theorem. So each time you have to compute the linearized operator. That's the main quantity. So this is what you get for the linearized operator. And you see that you have the time differential here, a transport term with variable coefficients, a Hilbert transform, which is the Fourier transform of the sign, let's say, the sign of the Fourier mode, and an operator here localized in the mode plus or minus 1 in Fourier, and it's given by this, like you have cos of theta and exponential I theta here. So it's localized in the mode plus 1 and minus 1. And the quantities which appear here are the conformal radius that I mentioned before. The conformal radius was linked to the Robin function here, so the log. And you have also the Schwarzian derivative of phi, which appear. So in the linearized operator here, and also in the V here, you have this G, which is linked to the Robin function and the Schwarzian derivative of phi. And the Robin function itself was linked to the phi. So everything here is related to the geometry of the domain. So at the linear level, really, you can encode the geometry in the linearized, everything is encoded here. Plus smoothing terms and small. So, so this is the shape of the linearized operator. In particular, you see that you have a degeneracy in epsilon in time, if you divide everything by epsilon. So you see that at epsilon equals to 0, you have, of course, here a degeneracy in time, but also you have a degeneracy in the spatial mode plus or minus 1, because this quantity, when you take the limit when epsilon goes to 0, you just have this operator. But the Hilbert transform and d theta coincide on the Fourier mode plus or minus 1. So this is exactly 0 on the Fourier mode plus or minus 1. So you see that there is a degeneracy here. Okay. Let's take a simple model. Like you take this. So basically you erase everything except the first transport term and the time derivative. So imagine you have a linear operator like this, and you want to invert it because okay, I didn't want to spoil, but I think it's the time to say it. You are solving this equation, right? Which is a quantity linked to the radial deformation of the patch here. And so you have g of r equal to 0. So you are looking for the zeros of a function again. So as we said, we linearize, and the linearized operator has to have a good structure, right? If you want to apply the implicit function theorem, this linearized operator has to be an isomorphism. If you want to apply the Kernel-Rabinowitz theorem that we had before, it has to be with kernel of dimension 1 and closed and codimension 1 range and etc. So there are really constraints. But here is even worse, because what you find here is that if you want to solve to invert this operator, so you solve this equation. You can solve in Fourier, and you have this expression. But here the denominator is really small. can be really small. And you have to quantify how small it is in order to estimate the HS norm. So you introduce a contour set which quantifies the values of lambda such that you can invert. And here, since you have an epsilon square in front of the time, you have to put a weight here, epsilon a bit more than square, to have a non-empty contour set and actually full measure set, or almost full measure set. And so in this contour set, you can invert L and quantify the HS norm. The HS norm of the inverse will be linked to the HS plus something, which is the quantity here of F. And you have an epsilon degeneracy also at the denominator here. So, so you have a loss of derivative here for the linearized operator, and actually you can prove that the linearized operator here has dense image. And to measure the set, to estimate the measure of this set, you assume, for instance, that this is Lipschitz in lambda, and actually in our case is analytic. And if you are able to quantify the derivative of omega from below, actually you can, by classical estimates on measure theory, you can estimate the complement of this guy, and you find that it is upsize epsilon to the delta inside this set. So you have an assumption here on the derivative of omega, but the derivative of omega is linked to the derivative of t, because omega was 2 pi over t. And so this is where you see where appears first the assumption that we had in the main theorem, which was the assumption on the period. If the period has is non-degenerate on the good range of energies, and then you will be able to have good measure estimates for the contour sets here that you need to invert your linearized operator because you're solving G of R equal to 0, so you have to run kind of Newton scheme, and so you have to invert your linearized operator. But this loss of derivative tells you that you cannot apply the classical Newton scheme, actually. And the fact also that the image is dense, you cannot apply bifurcation theory. So you are forced to use a Nash-Moser scheme. So I just recall here the Newton scheme, the classical one. So you take the iterates, Rn, where the next one is just a perturbation of the initial one, where you invert the derivative and you apply it to f at Rn. So this is the classical Newton scheme, which has a quadratic convergence. And to apply the Newton scheme, you have to have that this is an isomorphism. But this is not true here because of just the basic example that I showed you here. You have loss of derivative and degeneracy and blah, blah, blah. Oh, okay, here the degeneracy has no impact, but later it has. So you are forced to consider a modified version of the Newton scheme, which is the Nash-Moser scheme. And to apply it, you have to replace this guy, which is not well defined, by an approximate inverse. And you do it by truncated in Fourier. So your Rn here will be an approximation of your solution in the space where the Fourier modes are truncated to the level nn, when nn is growing super exponentially. And if you have good estimates on your linearized operator and on the inverse, like the one we have said before, so you have, of course, a loss of derivative, but the estimates are so-called tame, which means that in the highest norm, they are linear, the estimates, like this. then you can prove good estimates on the differences of Rn plus 1 minus Rn in HS, which is basically of this form. So you have a constant Nn to the power alpha, so fast increasing constant in n, but times the quadratic stuff in low norm and higher norm. So this is where appears the fact that you have to have linear growth in the high norm here, and also here. But so this is quadratic here. So it is basically corresponds more or less to your Newton scheme. But you have also this part where you have a really fast decay in Nn, but you have to reach a higher norm. So to make the scheme converge, you have to basically work with 3 levels of regularity. You have to work with the level of regularity for the convergence of the increments here. You have to have a regularity level for quantifying how much f of Rn is converging to 0, because you want to solve f of R equal to 0. And a third one, due to these estimates, you have to control in higher norm the iterates here. So you have 3 levels. 2 to control this guy in lower and upper norm, and one other guy to control how much f of Rn is converging to 0. And okay, but you can do it, and actually the scheme converges by induction. And this generalizes the Newton scheme. So it's a scheme which is really difficult to understand, but this kind of estimates is really the key. And the fact to understand that to get this kind of estimates, you have to have a linear growth in the high norm. So to have time estimates up to a loss of derivative, but it's not so dramatic because you can include them in the scheme here. So you have a quadratic convergence times a increasing sequence, and a decreasing sequence times something that you can control in high norm. And everything, if you put everything together, you can control the scheme and make it converge. Okay. But to apply this scheme, as the Newton scheme, you have to have a good first guess of the solution. So the first guess is, of course, if I take R0 equal to 0, but actually, if we compute everything, we see that what we should get for the Newton increments, or the Nash-Moser increments, is something which is exploding in epsilon, because G0 is of epsilon square. We have seen that if we want to invert the linearized operator, we have a loss here of epsilon minus 2 to the minus delta. So if you combine both, you have a loss here. So this is not a good guess to start. And so a first step to start the Nash-Moser scheme is to find a good approximate solution, and it's done by Taylor argument. I think I explained it here. Yeah, you do a Taylor expansion close to 0, and you want to kill the first terms which are not good, and you are led to solve this equation. And hopefully G of 0 does not contain the mod 1s, the mods plus and minus 1. So you can invert this operator and kill this term to have a higher order smallness. So this you can prove it. It's a computation in our case. Okay, so you can find a good approximate solution to start the Nash-Moser scheme. And so then you introduce a new functional which is renormalized according to this new first guess. And now everything is fine. You can run the Nash-Moser scheme. Okay, but to run the Nash-Moser scheme, as we have said, at least you have to find an approximated inverse to the linearized operator, because I said the Nash-Moser scheme here, you have to modify a bit here by an approximate right inverse. But when you want to do it, you will face this kind of problems, and you will have small divisors, so you will have to introduce counter sets. So in particular, you want to find the shape of this guy. This is the first guess that you need. And to find the shape of this guy, you have a procedure to follow. And the procedure is to reduce the linearized operator to the constant coefficient, at least at the main orders. So the shape before the linearized operator, so here's G is almost the same for F. You had transport term with variable coefficients, Hilbert transform, something with constant coefficient but localized in the mode 1 plus smoothing. So the first step is to kill this guy, to have constant coefficients here, because when you have constant coefficient, you just pass into Fourier and you apply this method here. I had constant coefficient, so I could really invert easily. There is no mixing of the frequency. There is no convolution in Fourier. And so the first step is to kill this guy to constant coefficient, and it's rather now understood procedure. You have to compose your linearized operator, conjugate, sorry, your linearized operator by a good transformation, which is a diffeomorphism of the torus, like this. And okay, here there is in our case, and also in the leapfrogging case, which our proof deals based its argument, there is a degeneracy in time that you have to tackle, and so okay, there is a degeneracy in epsilon, so you cannot really apply directly the method. You have to do a first transformation, but it's rather technical, so I don't insist so much on this part. Zineb can explain later if you want. So when you do this, you can construct a beta and a C such that in this contour set, you conjugate your linearized operator. So here there is B minus 1B, where the coefficient in front of the transport here is constant. It does not depend on the variable phi and theta. That's what I mean by constant. And so, so now you have an operator here, which is constant coefficient that I call L1 plus smoothing small perturbation. And everything which appears here again is linked to the so the function in the mode 1 here is related to the conformal radius and the Robin function. So all the geometry is preserved again. And now you want to give a perturbative argument to find an inverse to this guy. So what you're led to is to invert L1, basically, because this guy is an epsilon perturbation. So by, let's say, Neumann series, you can argue, provided that you can invert this guy. And so this is done by separating the mod plus or minus 1 and the other mods. So the phase space, you separate both. So you project like this operator now is with constant coefficient, so in Fourier is diagonal. So when you project, you have something like this, like mod 1 and mod orthogonal to 1. So to invert on the mod orthogonal to 1 is rather easy. You just have to introduce a new contour set. It's not a big deal. But the main point that I want to focus on is to invert the mod 1, because this is where the heart of the proof is. So to invert on the mod 1, what do you do? You want to solve this, like you want to invert, you want to find H. If you write what it means on the matrix of the Fourier mod 1 and minus 1, you are led to solve an ODE with 2 times 2 matrix. And so to understand it, you have a perturbation argument in epsilon, but basically you have this matrix A lambda, which appears. The A lambda that was really out of nowhere in the theorem. This is where it appears. When you try to invert this guy, you're led to solve an ODE, and the ODE is related to this matrix. or perturbation of this matrix. So you apply the Duhamel formula in some sense, and to find the periodic solution, because you want to invert in the periodic setting, because we're looking for periodic solutions. You can find a periodic solution if and only if this guy into pi is h of 0. So you can factorize here, and you can invert this matrix. If you can invert this matrix, you can find the solution. But to invert this matrix, if you write what it means, it's exactly to say that one does not belong to the spectrum. So this is where the spectral assumption appears. And so you can invert on the mode 1, you can invert on the mode orthogonal to 1, up to counter sets, and then you do a perturbative argument to find an inverse to this guy. So you have found an inverse to the linearized operator. So with a loss of derivative and blah, blah, blah. So you can run the Nash-Moser scheme and find a non-trivial solution to the original problem. And so you have solved the problem. That's it. Thank you.